we'll jump to chapter 12, partial differential equations. Okay. So we learned Fourier series expansion up to now, and we'll apply Fourier series expansion to solve some partial differential equation. All right? And then after we consider some partial differential equation which can be solvable by Fourier series expansion, then we will go back to chapter 11 to consider Fourier integral. Because in some partial differential equations, we need a Fourier integral to solve these equations. All right? So, so this is my plan. Okay, so now I jump to the early sections of chapter 12. All right? So the first section is about basic concepts of PDE. Okay? All right, so the distinction between ordinary differential equation and the partial differential equation is that for ordinary differential equation, we have only one independent variable. Okay, so we consider only derivatives. First, second, third, nth derivatives. But for partial differential equations, we are considering functions of several independent variables. So it means at least two. Right? And so we will consider partial derivatives right now. Okay? So this is the reason why we call it partial differential equations. All right. So let me list some important second order partial differential equations. So the following are important. Second order PDEs. For example, one-dimensional wave equation equal to here U actually is UTX. So U is a function of two independent variables. One is called the time variable, the other is called the x variable. Okay? So x represents the space variable, okay? And it is called one dimension because we are considering only the x coordinate. Okay, so it's called the one-dimensional wave equation. Okay. And in this wave equation, you can see that it involves the second partial derivative of U with respect to t, as well as the second partial derivative of U with respect to x. Okay, so you see that. So it is called the second order because we are involving second order partial derivatives. So it's called one-dimensional wave equation. And this equation, you will see this equation when you learn the EM wave, the electromagnetic waves. Okay? one-dimensional heat equation. Okay, so heat equation, sorry. It has two independent variables. One is time variable, the other is the space x variable. Okay, and the different side involve the first partial derivative with respect to t, but for the right hand side it involves the second partial derivative of u with respect to x. Okay, and because the second order is the highest order to take the partial derivatives, so it is called again a second order PDE. Okay, again the small PDE. And I believe that you encounter these heat equations when you learn physics. Okay, you are freshman year. Okay. So this is called equations. Alright? The third one is two-dimensional Laplace equation. Okay. Where the function u has two independent spatial variables x and y. Okay, so there is no time variable here, and this kind of equation occurs when you consider static electrical field. Okay, so if you want electrical field in the steady state, so that there is no time variation. So you have only the potentials in the space. Now, suppose we convert ourselves to two-dimensional space. So now you will have the Laplace equation to solve, to know the distribution of your electrical field. Okay. The two-dimensional Poisson equation. Okay, so you can see that the difference between the Laplace equation and the Poisson equation is that you have source here. Okay, so this is homogeneous, but this is not homogeneous. Okay. So homogeneous, homogeneous, homogeneous. So the first three are homogeneous partial differential equations, but the fourth one is not homogeneous. Okay, now two-dimensional wave equation. The two-dimensional wave equation is just the extension of one dimension into two-dimensional space. So okay. And in this case, U has three independent variables. Because wave, you know, in terms of wave, you know that you have dynamics. Okay, so the value depends on time, right? So this is the wave equations. Okay, so compare the two-dimensional wave equation with the one-dimensional wave equations. You can see that the only change is in the spatial dimension. Okay, three-dimensional Laplace equation. So again, this equation describes the steady-state behavior of the electrical field, okay, or magnetic field. So there's no time variation here. Just only, so the potential or the physical quantity U depends only on the point in the space, in the three-dimensional space. Okay. So in this chapter, we will try to solve these equations. Okay, these equations. And all right. There are some terminologies we may use later on. So let me see. Okay, so now a domain. So when we say a domain in an Euclidean space, n-dimensional Euclidean space, we mean that an open, connected subset. So for example, I think I mentioned connected set before, right? For example, in R2, okay, we say an open state. So for example, okay, this is an open connected state. It is open because that when you pick a point in the state, you can find a disk, okay, or a ball, open ball. So this one, so it says that maybe I will remark. Okay. A subset B is called open if for all points in U there exists an open ball there is an open ball. Okay. So if you find a point in this domain is an open set, right? So if x is here, maybe x is 0, I would say x is 0 here. So you have x is 0 here. Then you have an open ball. Okay. The whole open ball should be contained in U. Okay, so you can have the whole ball contained in U. Right? That is called open. What is connected or subset? U. Maybe I will use S of Rn is called connected if for any 2 points x and y in X, there exists a polygon not polygon, I would say there exists continuous piecewise linear maybe I would say this is a finite sequence of line segment of finite number of line segments connecting X and Y. Line segments is X connecting X and Y. Okay, so that means that if I select point, this is X here, and we have Y here. Okay, I will find a number of line segment. So probably from here to here to here and here. Okay, to connect X and Y. And the line segment should be all in X. Okay, all in X. So it's called connected. So, any questions about this two definition? Open set, connected set. Even though I just used R2 to illustrate the idea. So, do you have any questions about that? Okay, and now, next term, a region. All right, a region in Rn is a domain, okay, plus some O of its boundary point. So the boundary point here, right? Maybe when you include some of the boundary point, all the boundary points, then you will have a region. Okay? So I want to differentiate the two terms, region and the domain. The domain always open, okay? But the region may not be open, okay? Because a region is a domain plus some or all of its boundary points. Okay, now a solution of a partial differential equation in some region. We have to talk about regions. Why? Because that as you can see that all these functions involve at least two independent variables. So you have to consider coordinate spaces, okay? At least the two-dimensional or three-dimensional spaces. But in general, you may have partial differential equation involving a function which has n independent variables. Okay. All right. So a solution of a PDE in some region, say R, of the space of the independent variable is a function that has all the partial derivatives. Okay, appearing in the PDE in some domain. In some domain B containing the region R. And satisfies the PDE everywhere in okay. So let me illustrate the idea. Probably you find a solution of a PDE in some region. So you might, okay, for example, okay, so this is the region, all right? So you find a solution, okay, in this region. And this region includes the boundary points, part of the boundary points here. Okay, part of the boundary point here. Right? Now, so such a solution is a function. Okay, you will find a function. This function has all the partial derivatives appearing in the PDE in some domain D. So you might have a domain, for example, domain D. This domain contains all. Okay? Okay. And in this domain, all the involving partial derivatives, right? You should have all involving partial derivatives in D, in this open set. This open set. And often, the function is only required to be continuous. On the boundary of all of the region. Okay? And we'll have those derivatives in the interior of R, and we satisfy the PDE in the interior of R. So letting R lie in D, in the figure D, simplify the situation regarding derivative on the boundary of R, which is then the same on the boundary it is in the interior of R. Okay? So I'll just make a note here. The reason why I include it is because that when you consider boundary points, okay, it's very hard to consider partial derivatives along the boundary points. Okay, because to define partial derivative, you need an open interval, open ball to define it. So to include an open set of domain D here, now then all the boundary points of R, right, will be a point, interior point of D. So every point here you have you will have an open ball. Okay? You have an open ball, and in this open ball you can investigate this partial derivatives with no problem. Okay? So okay, so now partial derivative actually is more involved if we order to find the solution. So now in general, the totality of solutions of a PDE is very large. For example, the following functions u equal to x squared minus y squared, u equal to ex cosine y, u equal to sine x, vector parabolic cosine y, okay, and u equal to the natural logarithm of x squared minus y squared. These are solutions of the two-dimensional class equation. Okay, so we mentioned the two-dimensional class equation before, right? And you can see that the solution of two-dimensional equation can be these functions, and this function has very different nature. Okay, you can see that they are quite different by nature, right? So So the unique solution okay, of a PDE corresponding to a given physical problem will be obtained by the use of additional conditions arising from the problem. Because every problem should have a unique solution. This is the behavior of this problem. Okay. So to find a unique solution, you have to know the additional conditions. Okay, you have to know the additional conditions. Right, and these additional conditions should arise from the problem itself. Okay. Right, so quite often, for example, this may be the condition that the solution U assumes given values on the boundary of the region. And then we will describe them as boundary conditions. So we may have boundary conditions, okay? Or when time t when time t is one of the independent variable, okay? U or ut. Ut means the positive of U. over ut over force. Okay, maybe v squared. Okay, at t equal to 0, so we have initial conditions. Okay, all right. So the additional condition may be prescribed as boundary conditions on the boundary of a region, or prescribed as initial conditions if temp t is one of the independent variables. So, okay, so we will solve partial differential equations with some of these additional conditions. So either boundary conditions or initial conditions, or both of them. Okay. Okay, now the first simple theorem is called the fundamental theorem of superposition. Okay, if U1 and the U2 are solutions of a homogeneous linear PDE. Actually, the list of PDEs except the Poisson equation are all homogeneous and linear. Okay, so you can see that so they are homogeneous and linear. PDE in some region, or okay, so suppose we have two solutions of a homogeneous linear PDE in some region, or then with any constant C1 and C2, U equal to C1 U1 plus C2 U2 is also a solution of the PDE. Okay, in the region. Right, so this is the basic superposition principle. Okay. Just like we have such a principle for homogeneous linear ODE. Okay, so let's take an example. We want to solve uxx minus u equal to 0. Okay. Where u is equal to ux1. Right? Now, even though this is second order partial differential equations, but in here, the partial derivative is only involved with respect to x only. Okay? So, since it's simple, since there is no partial derivative with respect to 1. Okay? So we may regard u as a function of x by fixing. Okay, so we just by fixing the variable y, okay, as a parameter. Okay, so and now we have experience. We know a general solution of the ODE u dot parameters u equals 0. Okay, is u equal to a ex plus b e minus x. Okay, because the characteristic equation is not a square minus 1. So the root is 1 and minus 1. Okay, so you have the general solution like this one, where okay, a and b okay, are constants. For each fixed fixed value of 1. Okay. So for each fixed value of y, you have a and b, right? So that a and b, okay, maybe dependent, okay, on y. So that we put a equal to ay, b equal to by. Okay, and then u equal to a y ex plus b y e minus x is the general solution of the okay. So a, y, and by are arbitrary functions of y. Okay, and so the final solution is here, is this one. And when you substitute this solution back to here, you will find that this equation is satisfied. So this PDE is quite simple. Another example is to solve uxy plus ux equals 0. Okay, where u equals uxy. Okay, so now from here, it's quite simple. That from this, we can see that we can let px to be u of x. So we define px, and then we have y plus b equals 0. Okay, so it comes to like an ordinary differential equation. So this implies that p is equal to constant c minus y. Okay, right here. Where c is a constant Okay, for each fixed value of x. Okay. And we regard it as an ODE by fixing x. Okay? So when we fix x, we think about that this is just the ODE, right? With respect to y only. Okay? So we have this one. So the constant c is constant for each fixed value of x. So that c actually is c of x. Okay? Alright, so now p of x, y, which is equal to c of x, e minus y. Okay? But we know this is, okay? So we know that p actually is the positive derivative of u with respect to x. So this is implies that u is equal to p of x, y, and dx. Okay? So you have to do it. Okay. And plus dy, okay, plus dy here. Because this is the positive. So when we integrate over x, we have this constant. In general, it depends on y. And so we have p of x minus y. Okay, so now we have ax e minus y plus dy. Where a of x is equal to p of x dx. Okay, so it's the integral of c of x. Right? We have to know that ax and by are arbitrary functions. Okay? They are arbitrary functions. So the solution, you have a lot of solutions because you can put the arbitrary functions of x here, arbitrary function of y here. Okay? So the solution, actually the solution space is pretty big, right? Very, very large. Okay, so the second section, please read the second section because that the section describes a method to model a vibrating string. Okay, so it actually derived the wave equation, the one-dimensional wave equation, from scratch. And I believe you may know this wave equation from general physics when you were a freshman. And but I recommend you to read through section 12.2, okay? And to get a feeling, how do you end up with a wave equation to describe a vibrating string? Okay. So next week I will try to solve the one-dimensional wave equation. Okay, with additional conditions, especially boundary conditions. So any questions? Okay, so no questions. This is, and I'll see you next Tuesday.